Now we're going to talk a bit about continuity. So what is continuity? Well, if we think about it intuitively, a function is continuous at a point if you can draw the graph of the function in the vicinity of that point without lifting your pencil from the paper. So we can talk about continuity on some interval. So maybe between these values, if I'm drawing my graph, I drew that without having to lift my pencil. So that was a continuous curve, even though it may be discontinuous somewhere outside of that interval. There may be gaps, if you will. It would have been continuous on the given interval. So basically, a graph could be continuous forever, like a polynomial function in general, like this one might be cubic, or we could have a quadratic polynomial. Those would be continuous because I can draw them without having to pick my pencil up. But a rational function would have a discontinuity. I would draw my two hyperbolic pieces that are potentially separated by a vertical and a horizontal asymptote, and I had to pick up my pencil to draw that. So this graph is going to have a discontinuity. Let's think about a more precise definition for continuity. So we're considering continuity at some x value, which we'll call c just being some constant. So a function f can be said to be called continuous at some x value, x equals c, if you can satisfy these three conditions. One, the function value is defined. That means when you plug in an input, you get out a defined output value. You plug in x, there is a y that exists at that x. The limit as x approaches c of that function exists. And then the limit has to match the function value. So 1 and 2 have to give you the same answer. And if you can't state that the function is defined, A, and B, that the limit exists, and that C, the function value and the limit are the same, then it's going to be discontinuous at that point. So that's the long and short of continuity. Now, we have a couple functions that we talk about their continuity, and really when we think about continuity, another word we could use would be the domain. So sometimes you may be asked, say where this function is continuous, and essentially that's just saying what is the domain of the function, or on what regions can I draw it without lifting my pencil. So before we get into an example, I just want to look at some really common functions that we think about. So as I've previously stated, polynomials such as quadratic, cubic, quartic, etc. functions, those are going to be continuous for all real numbers. Any polynomial is going to be continuous everywhere. If we talk about a rational function, remember a rational function is a ratio of two polynomials, and we have a denominator. So essentially it's for any x except the values that make the denominator 0. So we say the denominator is not allowed to equal 0. So we would be looking at that rational function and saying, well, what value is going to turn the denominator 0? Because that's where I'm going to have either a vertical asymptote or a hole, which translates into a discontinuity. We also have here a root function, and this is actually an even root function. So a square root function looks like this. And when we're dealing with square roots, we know that the argument under the radical, specifically we call that the radicand, the radicand must be greater than or equal to 0. So we would be determining what values are greater than or equal to 0 and using that to eliminate the values for where the function is not continuous. So thinking about what you learned in your algebra class about domain, you did a lot of stuff with rational and root functions. Those were the two things. We said the denominator can't equal 0, and the expression under the radical has to be greater than or equal to 0, positive or 0. So this is just really a domain problem. Exponential functions are continuous everywhere, so there's no discontinuity. And then a logarithmic function, we just have to remember that the argument The value that we are taking the log of, that has to be strictly greater than 0 because logs have a vertical asymptote. All right, so as long as there's no log, there's no denominator or no even root in your function, you're probably going to have a function that is continuous everywhere or for all real numbers. So there would be no values that you have to omit. All right, so now that we've talked about continuity, we've talked about how continuity relates to the concept of domain, let's just do an example where we look at a graph and we determine whether or not the graph is continuous at a given point and how we would show that. So in this example, we're going to check for continuity using that 3-step test. And the 3 steps are to check that the function value is defined, check that the limit exists there, and that a and b, the function value and the limit, are identical. So first, let's consider at x equals 1. So 3 parts. Number 1, what is the function value? What is f of 1? And if I were to plug 1 into this function at x equals 1, the point that is defined is right here, y equals 2. So the function value is equal to 2. All right, the second part, let's check that the limit exists. So the limit as x approaches 1 of this function, what does that equal? So as we look at traveling across the graph or along the graph towards positive 1 from the left and traveling along the graph towards positive 1 from the right, we notice that the y value in this case is negative 2. So do 1 and 2 match? The answer is no. So the answer to the continuity at x equals positive 1 is that it is not continuous. The graph is not continuous. There's a hole here. If I were drawing this, I would have to lift my pencil and leave a gap there. So we draw that hole just to, really illustrate that it is a break in the graph. Okay, so let's look at one more point and then we will be done with our entire continuity lecture. So for example, B here, let's consider x equals negative 4. So the first part, 1, what is f of negative 4? And if I go to negative 4 in my graph and I look at the function, there's a solid dot. And just to emphasize, there are solid dots everywhere that there is not an open dot. So all of these are solid dots, but there's specifically a dot here at negative 4. So f of negative 4, my y value is 2. I'm sorry, negative 2. What is my limit as x approaches negative 4 for the given function? So as we approach negative 4 from the left and negative 4 from the right, we go towards the same point, and that is negative 2. Then step 3 says that 1 is equal to 2. The function value, negative 2, matches the limit, negative 2. So we would say that, yes, it is continuous. So it's continuous at x equals negative 4. And that's the answer. So that's continuity in a nutshell, if you will. And if you're asked to prove whether or not something is continuous, all you have to do is the 3-step test that we've looked at here. So now you're going to see other examples in your homework that aren't specifically going over this, but you understand the idea of continuity, and I want you to apply that thought to different types of problems. As always, reach out, let me know if you're struggling, because I would love to help you. Have a great day.